Hey everyone, it's time to talk all about software. Today we're going to be learning about clouds. Nope, not those kind of clouds. We're going to learn about the kind of clouds that you run software on. So if you're new to cloud technologies, say you've got a job interview coming up, you're in school, or maybe you're going to actually start working with them for the first time, stay tuned. This will be a perfect tutorial to get up to speed fast on what the cloud is and what cloud native is. So, without further ado, it's time to talk all about software. The cloud is a term that describes servers that you don't own or manage yourself. There's nothing particularly new or special here. Developers have been leasing virtual servers to run their software on for a very long time. But the cloud is a different kind of way to think about the hardware that your software runs on. Rather than worry about the underlying computers that your programs run on, the cloud is a way to treat a bunch of servers like an unlimited pool of hardware. No matter how many servers we have at any given time, we can almost think of them like a single giant computer that can grow as powerful or become as efficient as we need over time. This has made a huge difference in software development. In the past, developers needed to figure out upfront exactly how much CPU, memory, and storage capacity their programs would need. This was almost like a psychic effort, because it was hard to know exactly how powerful of a server we needed and how many servers we needed when we were also kind of guessing how many people would be using our programs over the future. This forced most companies to buy significantly more servers than they eventually needed, just to be on the safe side. Most of that computing power went to waste because on most days, your programs would only use a small amount of the hardware that you actually bought. And there is no real way to avoid this. Let's say that on most days your program needed one computer to run properly. But on a few special days of the year, your program needed 10 or more computers to run on properly. This is because on certain days, usage of your program may spike, and it may not be an exact science on figuring out how much it'll spike by. This is really common in industries like e-commerce, where on days like Black Friday and Cyber Monday, there's a huge wave of traffic to your website compared to the rest of the year. This can put a lot of strain on the hundreds of individual programs that make up a typical popular e-commerce site. To be on the safe side, programmers would have probably just bought 10 or more computers just to make sure that they had a little extra headroom. Most companies just left their programs running on those 10 computers all year, even though on most days all of that CPU, memory, and storage would have been completely underused. Actually, a good programmer would have probably bought 12 or even more computers just to leave a little extra headroom. Because if we got this wrong, our system would start to slow down, emit errors, or crash. This means that before the cloud, we might have a program running on 12 computers that really only needed one. And then on those few special days, we might use 10, but there's still a little bit of extra unused computing power there. But what if we want virtually unlimited power to run our software, but only pay for the exact amount of resources that we're using at any given time? The first company to realize the huge opportunity in all of this was Amazon. Jeff Bezos made a key decision in the early 2000s to start leasing out Amazon's extra server capacity to other companies, like Netflix. This decision changed the game for software developers, because instead of having to buy all sorts of hardware ourselves, we could actually lease just the exact amount of resources that we needed for our programs, only paying for exactly what we're actually using. This offering was called AWS, Amazon Web Services, and basically was the beginning of the cloud as we know it today. Now other companies have their own public cloud offerings, like Google's GCP and Microsoft's Azure. Aside from saving a whole bunch of money by only paying for what we need, what are the other benefits of moving our software to the cloud? Well, there's one huge advantage. Developers can treat servers in the cloud almost like a single machine with unlimited capacity, rather than having to worry about all of the individual machines that their programs are going to be running on. This means the developers can run their software on a computer as powerful as they'll need without having to guess up front exactly how many servers they'll need to run their software on. And if your program is written in a specific way, your program can even demand more resources, like extra CPU, memory, and storage capacity, exactly when it needs it. For instance, if you build an e-commerce site and a bunch of people visit your site all at once on Black Friday, the hardware that your program runs on can actually scale out to handle this demand by just grabbing more resources from the cloud. And then when the demand subsides, your program can actually release those extra resources, giving it back to the cloud, which is called scaling in. By scaling out and scaling in, your programs can be hyper efficient. The term for software that behaves in this way is called cloud native.
A cloud-native application is being designed to run in the cloud, and it can take advantage of the huge amount, virtually unlimited amount of resources that cloud platforms make available. But your software actually has to be built in a way that can actually harness this power. If you just build it in a traditional way, kind of like as an old school monolith, I mean, it's not like we can just move COBOL applications into the cloud and hope for the best, right? You actually have to build your software in a specific way to take advantage of the elastic nature of the cloud, how you can provision more resources and let those go as demand for your software ebbs and flows. If you recall from a previous video that I'll link right up here somewhere, you may remember that we talked about the software that developers write is turned into a set of machine instructions that your computer executes one instruction at a time in a loop called the CPU cycle. Here's where the cloud becomes really important and really interesting. If we only have a single CPU, we can only execute one machine instruction at a time. Well, what if we had an unlimited amount of CPUs? Imagine we put a whole bunch of CPUs together so we can execute more than one instruction in parallel. This is actually how most modern computers work. Your computer has a fixed number of cores. Each core is basically like separate CPU, but all cores are bundled onto a single chip, right? So now we have a single CPU with multiple cores that can run CPU cycles in parallel, and then they all share the same amount of memory and storage and all the other hardware on a single machine. Even cell phone CPUs have multiple cores now. You probably have a CPU with multiple cores in your pocket. For instance, the iPhone X has a hexacore processor with 6 cores, which means that it can execute 6 instructions at the same time. Having a multi-core CPU is critical for multitasking where many different programs may be running simultaneously. Remember, each one of these programs will be queuing up machine instructions at the same time. Without enough CPUs, all your programs will start to feel slow because their instructions are waiting and waiting and waiting for a single CPU to execute each one of those instructions. But let's say I want to connect a bunch of CPUs together to perform a common task that's really CPU intensive. Some of those types of things might be machine learning, AI, cryptography. What if we could harness the power of hundreds or even thousands of CPUs to perform one of these common tasks that would be virtually impossible on a single machine, actually be completely impossible on a single machine? Well, like I said before, we have to make some changes to the way that we write software to take advantage of this elastic nature that the cloud gives us. There are really 3 key rules for building a program that runs in the cloud. A cloud-native program is container packaged, it's dynamically managed, and it's microservice-oriented. The definition of what a cloud-native program is was actually defined by the CNCF, which is the Cloud Native Computing Foundation. The CNCF is a Linux Foundation project and aims to give all developers of cloud software kind of a common framework or understanding to work within. This helps to align software developers in the companies like Amazon and Google that are actually creating cloud platforms. Some of the most influential and impactful cloud-native technologies today, like Kubernetes, Prometheus, and FluentD, are now hosted by the CNCF. Let's describe the properties of a cloud-native system in a lot more depth. Let's start with container packaged. We need a way to package and ship our programs to the cloud. Containers give us a way of packaging our applications so they can be shipped, like how we would load cargo inside of shipping containers. We want to ship our program to the cloud, so first we need to package it inside of one of these containers and then transport it on the cargo ship. Once our program actually makes it to the cloud, it'll be dynamically managed by the cloud's infrastructure. If you remember in our previous video how your operating system manages the execution of CPU cycles, now imagine that we may be shipping hundreds of programs that need to run on hundreds of computers. Some type of manager will need to decide where the contents of each container are shipped to and exactly how they're executed. Finally, a microservice-oriented architecture is necessary to make the most out of cloud hardware. The reason for this is we don't want to build our system as like one giant program and ship it off to the cloud. There's really no way that the cloud can slice and dice your program after the fact in order for it to run efficiently. The reason that we adopt microservices is because each component of our system is going to have different hardware needs. So as you can probably tell, microservice architecture is meant for bigger systems. Like if you're creating a blog for your dog or your cat or something like that, you're not going to want to go full microservices in the cloud and all of this, right? But if you're getting a job and you're working at a bank or something, yeah, you're going to definitely want to understand how cloud technologies work and how microservice architecture fits into that. So in a future video, we'll definitely cover microservice architecture in a lot more depth. Also, in our next series of videos, we'll cover other things that are definitely related to what we just talked about, like container management platforms, things like Kubernetes. We'll also talk about new emerging technologies like serverless. You know, we're just booting this channel up and I'm going to be creating a lot more of these tutorial videos. So if there's something you'd like to see, leave a comment. And if you like this video, hit that like button. And if you want to see more videos just like this, don't forget to subscribe somewhere down below. Thanks for tuning in, eh?